Yeah, thank you. Yeah, so today I'm going to talk about how we accelerate vLLM with LMCache. And basically, after this little talk, you will know about why to build LMCache at the first hand, and what's the functionality and the optimization behind LMCache and the performance benchmarks. Yeah, so now let's start. Okay, so just want to do a quick survey. Does any people here does not know about KV caches, prefill and decode? Is there anyone? I see. There's still some people. So let's do a quick round of introduction. So basically, the large language models in inference are separated into two stages. The first stage is called prefill, where prefill basically let the large language model read the whole input and generate one single output token. And for decode, it just generated one more token after previously generated tokens. But the key thing here is that there's a special data here called KV cache. And this KV cache is it's more like a materialization of large language models computation, where you can reuse it afterwards. Yeah. So and the whole LMCache is built central around this KV caches. So for now, please treat it as a cache that you can read to accelerate your application. And that's enough for today's talk. Let's start. Okay. So here is the table of content. And the first question is why LMCache? Why do we need a thing for the LM inference era? And the second question is how to use LMCache, the usage. The third part will be the system optimizations that we already built. And the fourth part will be more on the machine learning optimizations plus system optimizations that we are currently building. Yeah, let's start. Cool. So let's start from the motivation of LMCache. The goal of our LMCache is that we want to build the fastest open source solution that connects inference engines and storage hardwares with KV caches. So it's more like a connection between the engine and the storage, but the connection is done through KV caches. Okay, and why do we need such an open source project? So the first motivating trend is that KV caches are getting larger and larger, and it's exceeding GPU capacity. So basically, we found that there's an underlying trend that the KV caches are scaling pretty rapidly. So at 2024, GPUs are typically enough for KV caches, but starting from this year, Q1, we start to see people requiring CPU RAMs for KV caches, and this Q2, we start to see use cases where people use SSDs, local SSDs for their KV caches, and now we are seeing people are using object stores, and for example, we are collaborating with CoreWeave, and we are using the CoreWeave AI store to store the KV caches. And we are envisioning that the KV caches will be essentially cross-cloud, and it will be a huge infrastructure. And that's why we need a project for this. Yeah. And basically, this kind of KV caches as a data is very difficult to handle, because unlike traditional web or text data, KV caches are much bigger tensors. So typically, because for example, we have maybe for each request, we'll have thousands of tokens, and the size of the KV caches typically scales to the scale of gigabytes, and it's just for one single request. Imagine how many requests are running in your system, and the real-time generated KV caches can be really large. It's a huge tensor flowing in your system, and that is not the use case scenario designed for traditional storage. So we need the infrastructure. And as a result, it's basically more and more KV caches. It needs to be stored in external storage, not in GPU, not in CPU, or not even in disk. It's in a remote storage. So yeah, that's the first trend we are finding. And the second trend is that KV caches per token is actually getting smaller. And this is done by, there's two phenomena here. So first is that attentions are using less KV caches per token, starting from the start from the traditional MHA, and then we have a group query attention, which it reuses the KV caches for different query heads and makes the KV cache smaller. And we have MOAs, and this is done by DeepSeek models, and this one is even less KV caches per token. The second trend we're observing is that there's sparse attention using in existing models. And for example, in this short example, we are contrasting between traditional model on the left side and the sparse attention model on the right side. So we can see that for traditional models, every token, every layer has KV cache. But for the sparse version of the model, there are a lot of parts, and for a lot of tokens, and for a lot of layers, there's no KV caches required for inference. And that results in average, you have less KV caches per token in average. Yeah, and we found that this trend is not a coincidence. So basically, this trend is because people just want to fit longer and longer context inside their limited GPU memory for like more and more complicated workload. So this is just a natural result of that trend. And what does this mean to the KV caches as a data? It means that the loading the KV caches for the latest model is 10x faster than traditional models. Yeah, it's just because the attention data per token is getting smaller, loading the same amount of KV caches, loading the KV caches for the same amount of tokens are simply getting faster. And this makes storage really a feasible solution because it is faster. Yeah, you can load the data faster, it reduces your TTFT, it becomes faster than prefill, and it just starts to become economic. Okay, so these are two motivating trends that for us to build this LMCache, the de facto standard for the KV caching in open source. And to draw a simple layering figures to give you guys a sense on where LMCache is located. So basically, the top level will be the distributed serving framework, production stack, Dynamo, LMD, Kserve, and also Rayserve. Oh, I should draw Ray here. Yeah. Okay. Yeah. And the second level will be the LM inference engines. And currently, vLLM and sklearn are the two major parties in this game. And underlying the inference engine, we're envisioning there will be a KV caching layer where it's simply just moving around your KV caches. And LMCache is built for this. Okay, and the trend, like we are putting some numbers here to support that we do need a separate layer for this. First is that thanks to the popularity of LMCache as open source project, we are receiving over 300 terabytes KV caches data, and also like 1.28 billion hit tokens per week. So it's like 300 terabytes. That all sounds like a huge data, but it definitely cannot fit into GPU. Yeah, and we also have like 100 plus contributors from the global AI community, like from China, from US, and from all kinds of places. And also we already joined the PyTorch ecosystem project. So yeah, and it will remain open source. Okay. And also, just want to give a context is that we received like 5.5K GitHub stars in less than 1 year, and compared to those popular similar open source projects, we are having more stars than them. Yeah, for example, like maybe it's not good to compare with them. Yes, yeah, but just as a context. Yeah. Okay. Let's do a quick overview. Yeah. So basically, like from a system perspective, let's take imagine a system figure here. So on the top there will be an inference engine, and then we open up an API to connect vLLM to our LMCache, and behind the LMCache it operates between two different types of data, two different types of media. One is like media set attached to the local node, for example CPU and DRAM, CPU and disk, and also there's remote things that we also have a separate component that operate on the remote part of the data. For example, it can be a remote server, Redis, Valkey, Infinity Store, Mookie Store, DFS, and of course there will be Ray, and we are working on it. Yeah, and also we have like more collaborators, like for example Weka and the Samsung SPDK and GPU Direct Storage and many more. So yeah, you can see that like there's a lot of different techniques happening on the storage and on the storage layer, and we're connecting it to the inference engine. Okay, and here is a quick adoption, showing that how many companies are using LMCache for now. So we have design partners listed on the left side, and we have early adopters listed on the right side. Yeah, so a lot of huge companies are using LMCache. Okay, and they use LMCache for a reason, because we deliver best performance. Okay, my animation is like, yeah, okay. So basically the workload is that we are using a simple Llama 3.1, and we are doing like a fixed input length and fixed output length query, and we assume that we have 40 users, and we have like 20 rounds conversation per user. And compared to the commercial alternatives and compared to vLLM, we are achieving 5 to 10x faster TTFT and 2x faster inter-token latency and a higher request rate. And interestingly, the best commercial baseline here, which is the commercial 3 colored in like blue, is using an old version of LMCache. So they're using our software to compute with us. Yeah, but yeah. Okay, so here's the performance figures. And this is not doable without a community in open source. So I'm listing several important several contributors that several contributors, and there are many, many more, and we love them. Thanks for the contribution. And I listed their contributions here. For example, the observability, SLAN integration, and different support for like the storage and for the hardware, and also for model support. And thanks to all of them, they make LMCache practical. Thanks. Okay, and yeah, now I finished the part of like why we have LMCache as a project, and just want to quickly show how do we use LMCache as a user. So for the single node deployment, like we are having a very simple API where you can simply specify the KV offloading backend to LMCache and the KV offloading size to size in gigabytes, and this will turn on CPU offloading for you. For distributed scenario, of course, distributed thing is always a tricky thing, but we try to make it easy through our own vLLM production stack project. And we have Helm charts available for Kubernetes version of distributed deployments. And we are also working on a re-version of the distributed deployments. Yeah, and because we know that LMCache is tricky to deploy, and for different clusters, you need different storage solutions. You have different limitations. For example, I know there are multiple clusters that does not support NIXL, and yeah, so there's different limitations. We help you handle distributed deployment of LMCache, best utilize your cluster's hardware, and please contact us through this email. Okay, yes, starting the add moment. Yeah, and the easiest way to using the LMCache is through our like SaaS project. So basically here, like you can choose, through our SaaS, you can choose GPUs from different providers. And we're integrating with Lambda and Nebius. And the GPU is pretty cheap. Thanks, Nebius. Yeah. And deploying LLMs is very easy through just clicking. For example, we can deploy a quad model by clicking, and then we can fill the name and fill the target cluster, which is the GPU cluster you like, either Nebius or Lambda. And then you can click and then wait for 4 minutes for it to launch. A bit long, but 4 minutes is much shorter than you yourself deploying it on your own cluster. And it's ready to serve and chat. Yeah. And we are hiring. Yeah, here's a list of like the positions we want to hire. And please contact me or email contact@tensormesh.ai. Yeah, and thanks for ad time finished. Okay, so let's start from then let's dive into the system optimizations of the LMCache. Like what makes the LMCache such a performant object, such a performant open source project. Okay, so imagine that basically LMCache serves as a bridge between the inference engine and storage. So there will be like a northbound API to the inference engine, and there will be a southbound API to the storage. And for the northbound API, the challenge is twofold. First, how do you co-evolve with the inference engine? Since the large language model is such a fast-pacing space, how to co-evolve with the inference engine is a very important practical concern. And also, performance-wise, how do you saturate PCIe bandwidth without interrupting GPU computation? And this is basically all the engineering magic that we do there. And for the southbound API, which is a storage library integration, and the main challenge is basically how to saturate the storage libraries IO bandwidth, maximally saturate them, like let them load KV cache as fast as we can. Okay. So the first challenge is that how do we co-evolve with inference engine? And this is really based on a really practical need. The need is that different clusters and different companies, they need different KV cache offloading or loading solutions because their clusters are just different. They need different solutions. And there's like traditionally people handle this like different solutions. The traditional way is to build a standard, and but for large language models, since it's pacing too fast, building a standard is too slow. And we also tried to patch code into vLLM. Like basically, we have a local patch in our GitHub repo and let user patch it. But in practice, every company wants to do some twist to vLLM, and this twist is typically not compatible with our code patch. And so basically, we want upstream compatibility, and this is not doable by patching. So our solution is that we ship public API into vLLM. Basically, we build a like public API set into vLLM and maintain it, and that's the approach we're taking. And yeah, I guess that's one of the key components of making LMCache successful, because like people in the open source, like people typically don't take that route. They don't build public API in another open source project, and we did it. Yeah, why we did it? The first reason is, of course, there's a strong need behind the community that requires this API. And the API example are PD disaggregation and KV cache offloading. And also, we are designing this API that complies with vLLM's design philosophy. Yeah, because I was like working with vLLM core team for like about a year, I kind of like I'm pretty aware of their like design philosophy, and I'm designing the API to be fully comply with that. And that protects the API from the evolving of inference engine, because the design philosophy typically don't change that frequently. Yeah. And what's the design philosophy behind vLLM that we are leveraging? The first simple one is like there's a scheduler worker separation in the current vLLM's core. And yeah, basically, and this scheduler worker separation is based on two needs. The first need is that you need to manage the KV cache as a huge object inside GPU. That requires a scheduler. And the second need is that you want to distribute your model across GPUs, and that requires a distributed version of worker. So basically, there's no like, so basically in this architecture, we have two roles, scheduler and the worker. And the first insight is that we need to have scheduler-facing API and worker-facing API. It cannot be just facing worker or just facing scheduler. It needs to be facing to both. That's the first thing we did. The second thing we did is that as scheduler, we found that there's a key abstraction that vLLM is using to implement functionalities, which is prefix caching. And for example, in this figure, like in old vLLM core, they're implementing different functionalities separately. For example, parallel sampling is implemented using a lot of like bunch of code, and preemption, they have implemented like a complicated swapping logic, which hurts the scalability of project, and of course, prefix caching itself. But starting from the new version of core, vLLM starts to implement functionality on top of prefix caching. And this makes a prefix caching a very special feature that if we could hide our KV cache transfer behind the hood of prefix caching, we can easily achieve feature compatibility. In LLM, feature compatibility is just very important. You want to speculative decoding, like you want to turn on your chunk prefill, and all that things are compatible with prefix caching by design. And if we are hiding the API behind the prefix caching, we are automatically compatible with those features. The third part of like this part will be about the workers design. And for vLLM's workers design, there's a special thing called piecewise CUDA graph. And traditionally, like in older vLLM core, the whole model forwarding is captured in one single CUDA graph. This basically, it gives you performance, but it trades flexibility of injecting operators. Where we have API because we want to inject operators. We want to inject GPU operators to move the KV caches in and out. But now, because of this piecewise CUDA graph, attention operators are executed in eager mode, which means that we can inject GPU operators before and after attention without breaking CUDA graph support. And this gives the best performance without breaking, like, because CUDA graph is just so important for like different performance optimizations. And like the talk previously also mentioned CUDA graph. And almost every LM talk mentioned CUDA graph. So it's just very important. Okay. So let's take a quick look at the interface. And by awareing of those all kinds of designs, our APIs are two sets, scheduler and worker. As scheduler, we have a prefix caching API where we ask how many new KV hit can be achieved by having the connector. By the way, we are calling our the API connector API, KV cache connector API. Yeah, so connector just refers to the API. Yeah, and we are planning the KV cache movement GPU ops after the scheduling, because we need to prepare for all kinds of GPU ops and plan them ahead. For the worker, we are having APIs before and after forwarding and before and after attention. So basically, our API provide a series of hooks for the implementation to call and to hook into new GPU operations, and this facilitates them to for example, load and offload the KV cache, achieve synchronize with the main inference stream, and trying to overlap with the commutation. Okay, and this is done by this is the philosophy part, and then let's dive into some real engineering thing we are doing. So basically, the second challenge is how to saturate the PCIe bandwidth without interrupting GPU computation. And I'm separating this to two small challenges. The first challenge is how to move paged KV cache faster. And second one will be how to loading or offloading KV caches without interrupting GPU computation. Okay, so because vLLM is basically it was originated from paging the KV cache using paged attention, the KV caches are just a series of small pages, and they are not contiguous. So if you're directly using CUDA copy async, it will be very slow because you have so many pages. For each page, you have to launch a kernel. It's very slow, just too many kernels. Kernel launching overhead is too large. So we are writing our customized CUDA kernels to accelerate the KV cache loading and offloading on paged version of KV caches. The second one will be how to loading KV caches asynchronously. And this one, interestingly, it's not a single problem because the bandwidth of CPU memory and between the CPU memory and GPU and the bandwidth between CPU memory and storage are just so. So between the CPU memory and the storage, we are using request level async to achieve the best asynchronicity. And between CPU and inference engine, we'll use layer-wise pipelining to achieve the best asynchronicity. Okay, so let's give a quick example on the request level async. So for example, here our key design is to allow vLLM to skip the scheduling of one request if the scheduling API returns null. So for example, we call the getNum new call this scheduling API, and because we are not loading the KV caches from the remote storage to CPU yet, it will launch a loading operation first and return null. Let's say loading takes this amount of time. And then we call, in vLLM's next iteration, it will call the scheduling API again. And then, because the loading is not finished, it will still return null. And at the next iteration, it will call this API again. And now, because the loading is finished, we are returning the actual number of how many tokens are hit inside LMCache. And then after this, the whole vLLM knows there's an external prefix cache, and it can load it and let it participate into the request execution. Okay, and to contrast between with and without request level async, on the left side, without request level async, the total execution time is 86 seconds. And with the request level async, the execution time is 79 seconds. And you can also see that without request level async, because there's blocking load, the inference engine are the graph is just so aligned because there's blocking calls there. But with request level async, because it's more asynchronicity, there's no strict alignment between requests. Yeah, and that's what we want, because no strict alignment means higher asynchronicity. Okay, and also we're implementing layer-wise pipelining, and this one is just a whole bunch of engineering. So not too many interesting technical insights. So I'll just put the numbers here. So basically, here we are taking offloading as an example, where because offloading is simply you are moving KV caches, you're copying KV caches to the storage, so it's purely adding overheads. And by evaluating this scenario, we can see that how many overheads we are creating. So, for example, traditional inference without any CPU offloading takes 3.8 seconds, And the CPU offloading without layer-wise pipelining is adding about 0.3 seconds overhead, 10%. And with layer-wise pipelining, the overhead reduced to like about 0.085 seconds. And this is like almost like 4x to 5x smaller overhead compared to previously, and resulting in like just 2% to 3% overhead of the whole execution. And we also did NSYS profile. So basically, we can see that the upper part is vLLM kernel launch. The latter part is like, the bottom part is like KV cache offloading. And basically, what we want to show is that these two streams are executed both executed. So basically, we are fully utilizing the computation of vLLM and also the memory bandwidth for KV cache offloading. Okay, and the third challenge will be how to fully saturate storage bandwidth. And we have like different techniques here. For example, we do batch operations to reduce RPC overhead for storage libraries. And we are also doing zero CPU copy by copying data directly into LMCache registered memory space. And this requires tight collaboration with storage vendors. And thanks to all the storage vendors that help us achieve this. And I'm skipping this part due to time constraint. Okay, and the last part will be the machine learning optimizations. Oh, there's only, yeah, due to time constraint, I'll be really fast, but yeah, I have too many contents set. Okay, so why do we want to have machine learning optimizations on the first hand? It's simply because we are working on machine learning workload. And in this machine learning workload, the KV cache is a tensor that can be changed. It's not an immutable object, it's a mutable object. And that gave us a huge round of potentials of achieving fancy optimizations. So first, we have KV cache compression, our cache gen, which is already deployed in production. Second one will be the infrastructure for token dropping. And the third one will be efficient KV cache loading for sparse attention. And the first one is KV cache compression. At the high level, it serves as a SerDes, basically a serializer and deserializer for KV caches. And we are achieve a significant compression because there's continuity of KV caches between tokens. So for this figure, x-axis is the tokens, y-axis is different channels. And I'm not sure you guys can see it, but there's like horizontal artifact. And that signals the KV caches are somehow continuous in the token dimension. So we can take we can use different space encoding. And also, we found that the different layers layers are not built equally. Later layers are much less sensitive to quantization because if you quantize for example, if your model is 80 layers, you quantize the 79 layers, your error only affects one layer at most. But if you have 80 layers and you are quantizing the first layers, the error will propagate through the whole model. So later layers are much less sensitive to quantization. And this technique is now running in Bloomberg's production. Okay, and we are also working on framework for token dropping. Due to time constraint, I'll skip this. Yeah, we are working on a framework to support token dropping. And also, we are supporting efficient KV cache loading for sparse attention. And this is because of sparse attention, not all KV caches need to be loaded. There's a lot of space to save. For example, let's take a look at this model where the top layer and the third layer are using Mamba KV cache. And for Mamba, you only need the KV cache for last token. And the second layer is using sliding window. For sliding window layer, you only require the KV cache inside sliding window. So basically, there's a lot of KV caches that does not need to be loaded. But actually, this is what existing frameworks are doing, like existing frameworks across open source. They're loading every KV caches. And this is not ideal because ideally, we just want to load KV caches for inference. We don't want to load KV caches that are not related to inference computation. And this technique merely can give us 4x improvement on long context because a lot of models are using sparse attentions like in a 4 versus 1 ratio, where 4 is the number of sparse attention and 1 is the number of full attention. Okay. And also, we are extending the boundary of KV cache reusing. So traditionally, KV caches can be only reused as a prefix for the same model. So there's two limitations, prefix and same model. And we show that both of these limitations are breakable. We can do caching at any position and across different models. To achieve caching across any position, we have a word called cache blend. So basically here, let's take a document QA as an example, where the first doc is prefix, but the second doc is non-prefix. Traditional work will just do prefix caching, where it just have the KV cache of the first document and reuse it. This is not ideal because it need to recompute for the non-prefix part, which is the second document. But our work will reuse the KV caches, but correct it with a sparse cross-attention recomputation. And this cross-attention, because it's really sparse, it can be recomputed very fast. So we are still spending some extra computation, but we can reuse the KV caches of both documents to accelerate our whole LLM inference. Yeah. The second technique is called droid speak, which is reusing KV caches across model. So basically, in traditional prefix caching, it is directly reusing all the KV caches. But we found that by selectively recomputing a few layers, we can perform prefix caching across different models. Here, we only started to explore like the models fine-tuned from the same model, but it's already a pretty popular use case these days. And we are further working to try to reuse the KV caches between models models with different architecture, but it's still a lot of future works. But at least it's possible. OK, and as a summary, so basically, we aim to build the fastest open source solution that connects inference engine and storage hardware with KV caches. And please try our SaaS product to test out easily without installing LMCache on your own. And we have best KV caching performance by system optimizations. And we also are inventing like machine learning optimizations to unlock the full potential of using KV caches. And that's all. Thank you.
Talked about the vLLM thing. Yeah. Is integrating with SGLang is the similar approach, like APIs?
We already have integrations with SGLang, yeah.
With the similar approach, like?
Yeah, by defining a set of APIs, yes.
Got it.
Are there any other questions from the audience?
Hi. So for the more commercial offering, does that work with other like systems like NVIDIA Dynamo or?
NVIDIA Dynamo is using LMCache, so yes.
Yeah, but I mean for the more paid offering that has like all of the latest and greatest optimizations.
I see. So for the latest offering, we are not using a like global orchestration framework for now. We are adding support for that. Currently, it's more like it's instance level, like Bootstrap. Yeah.
Hey, thanks for the talk. I guess the PCI bandwidth to the CPU is quite important, and you talked about writing your own customized kernels. I found in my experience, like using nickel to go to PCI, using the doesn't actually reach the full bandwidth for the PCIe.
For decode or?
No, just like trying to offload it, just like a straight update or offload. For some reason, like I don't know why, but I found that using memcopy was a lot better for getting the bandwidth. But now you've rewrote it. I wonder if you have any like insight into how you can sort of like.
I see. So you like just want to rephrase your question. So you mean like you're observing that your memcopy is not saturating the PCIe bandwidth.
No, memcopy does saturate the PCIe bandwidth, but like kind of nickel operations don't. When I offload, sort of we're using nickel. So my question is, you wrote custom kernels because now that's a contiguous memory, but now you have non-contiguous because you're using the KV cache.
I see.
So I'm saying, how could I now? Like I'm just looking for some insight in how to use it.
I see. So in our solution, we're doing a D2D. We are doing a D2D copy first to make it contiguous and then offload.
Okay, that makes sense. Then.
Yeah. Thanks for a wonderful talk.
Thank you.
Fantastic talk. I was wondering, where do you see this space going over the next few years? And if you could share a little bit more about droid speak. Do you think that KV cache is going to be a primary modality for intermodal communication?
That's why we built the company. Yes, we believe so. Yeah.
Okay, if there's no more questions, one more round of applause.
Thanks for coming.